So at the LHC, we collide these very large ions with very high charges. So they're moving at ultra-relativistic speeds, and the electromagnetic fields produce a very intense flux of photons that have incredibly small virtualities. So these are effectively real photons. And the intensity scales as z squared for the flux corresponding to each nucleus. So this leads to an enhancement of 82 squared for gamma A processes, where one nucleus emits a photon, that photon strikes the other nucleus, or scales as z to the fourth in the case of gamma-gamma processes. So you'll see huge rates for 2-photon production of things like dilepton pairs or whatnot. So we have these very large photon fluxes. So you can effectively treat these ion collisions at the LHC as a beam that provides a high number of very energetic photons. So we're looking at effectively photon scattering. Now you can get the kinematics of these photons from some pretty basic uncertainty principle estimation. And the really nice thing here is that the transverse momentum of the photon doesn't get boosted, but the longitudinal or the total energy does. So you have a very energetic photon with very little total transverse momentum. So you're looking at very clean signals where you expect everything to be balanced in the transverse direction. So these processes have been explored very heavily over the course of a number of years. So I'd like to kind of organize it in this way. So here I'm showing is a table. On the left, the different kinds of photoproduction collision systems which have been studied in UPCs, and then a whole set of final states. And I'm showing all the different experiments that have measured this. So over the course of the last 2 decades or so, there's been a huge proliferation. I'm being a little unfair in this table in the sense that vector mesons represent probably the majority of all measurements in the field, but I've marked it as one column here. But these other final states, things like dilepton production, photon production in a gamma-gamma to gamma-gamma light-by-light scattering process, jets, hadrons, and exotic searches, we've really seen a proliferation of these ultra-peripheral collisions as a novel way of probing a huge range of interesting physics. This is everything from precision standard model physics, exotic searches, nuclear physics at low X or diffraction. And the thing that I'm going to be focusing in on today is this new ATLAS measurement, which is of jets. And the interesting thing about jets is that by producing them in a photon-nucleus collision, you strike the nuclear target, you probe the parton distribution within that target, and you can effectively map back onto the distribution of quarks and gluons inside of the struck nucleus and have a very clean, precise probe of that nuclear structure. So that's going to be the aim of the measurement that I'm showing today. Now, a bit of background on how we actually do this. So here I'm drawing the 2 dominant Feynman diagrams for this photonuclear jet production process. On the left, we have what's called the direct process, where the photon interacts itself with a parton within the nucleus. Or you have what's called a resolved process, where the photon fluctuates to some virtual hadronic state, and then some constituent of that hadronic photon or that hadronic fluctuation of the photon is what actually strikes the nucleus. So both of these processes contribute, and in both cases, they strike a parton in the target. And that's really what we're after, is that capacity to strike this parton and reconstruct the kinematics of the different partons within the nucleus. So the way that we do this is by measuring jets. In both of these 2 processes here, you can see that you have outgoing partons, quarks, or gluons, and those are produced at quite high energies. So what we're able to do is reconstruct the sprays of hadrons that these produce, commonly called jets. And those jets that we reconstruct map back onto the partons that are coming out of the hard scattering, which give us information about the kinematics of the initial state, the parton and the photon that enter into the collision. And here I'm just showing for kind of information about how well this really reconstructs back. If you look at the Q of the hard scattering, so this is the Mandelstam T in kind of if you're talking about the hard scale of the scattering process, and if you look at the relationship between that and HT, which is the sum of all of the jet momenta, it maps on really effectively. So you see there's a very tight correlation between HT and about twice Q. So the jet kinematics kind of cleanly get you a way to access the kinematics of your hard scattering process. Yeah.
So there's a byte missing out of the byte.
Yeah, that's just a feature of the Monte Carlo production. We had to kind of cut it off in a certain range. Yeah, so it's a little unsightly, but it's just how we produce the data to make this. So if you actually look at the kinematics of the final measurement, you can see where we're targeting. The really nice thing about these ultra-peripheral collisions is that aside from having this very clean system where you're using a photon to probe the nucleus, they also have very weird kinematics. They're not standard for the LHC. When the photon strikes the nucleus, it's a very asymmetric system. The photon has much less energy than one of the two nuclei. So you're able to probe a wide range in Bjorkane X and in Q squared, which covers a kinematic range where there's very little existing constraint. So here I'm making a plot comparing existing world data going into nPDF fits. And then in red, we have the coverage of the data that I'm going to present. And you can see that it's extending us out into a range where we really are seeing something new in nPDFs. So that's the reason why we're interested in this. Now I want to start talking about the nitty gritty of how we actually do this measurement. So we do it with the ATLAS detector, as I mentioned. One interesting thing about this photonuclear jet production process is that it's an inclusive process. So you strike the nucleus, you break it up, it fragments and produces a large number of hadrons, which occupy a large part of the detector. And that's a big piece of how we select these events. But because of that, you need to be able to reconstruct particles over a wide range in rapidity. And on top of that, we have to do full jet reconstruction, which requires using the electromagnetic and hadronic calorimeters in ATLAS. So we really kind of use the full detector capabilities in order to do this measurement. We need all of the tracking, which allows us to reconstruct charged particles. We use the electromagnetic calorimeter specifically to separate out contributions from things like electrons to prevent you from getting fake jets. And then the hadronic calorimeter for measuring the full hadronic jets we need. So we have nearly 10 units of rapidity coverage in ATLAS. You're able to measure from -4.9 to 4.9 in Ada, and that's really important for being able to do this measurement effectively. So here's what one of these events looks like. So here I've kind of mapped out on the top our the general timeline that we're going to follow in doing the measurement. So we start from just a sample where we require some kind of jet trigger in order to tag the events and collect our data sample. Here's an example photonuclear jet event display from our recent 2024 run. So this data was taken 4 months ago, 5. So this is a little bit newer than the data that I'm showing for the results, but it's a particularly nice event display. So generally the features of these events, right? You have nothing going on one side of the detector. On the side where you have a nucleus which emits a photon, that nucleus doesn't break up, it doesn't produce any particles, so you get nothing. It'll go away. Okay. In addition to that, you have jets, but the jets are really are pushed towards the nucleus going side of the detector. Because again, the photon has much less energy than the nucleus that emits it. So when the photon scatters off of a parton within the nucleus, it biases the center of mass energy towards the nucleus going direction, so you see your jets shifted forward in rapidity. And then you have a bunch of other particle production on that side of the event, the side with the jets, because that nucleus does break up. So it produces these fragments that you're able to measure and see. So after we have our jet-triggered sample, let's talk a little bit about using the characteristics of these events, how we actually are going to go about selecting them. So here I'm drawing a map. On the x-axis, we have pseudo-rapidity eta, on the y-axis phi. So this is kind of a map of the ATLAS detector. And this is kind of a characteristic photonuclear jet event to help guide how we're going to select these out. The black dots represent individual particles that are produced, and the blue circles are jets. Additionally, the photon is going in the positive direction. The nucleus is going in the negative direction. And you can see that because this nucleus breaks up, it produces forward neutrons, which we tag on that side of the detector. So that forward neutron tagging is the first thing, and it's very important. So we look in each of our collisions, you can see that one nucleus breaks up, it produces some number of neutrons, we call that xn. And the other side, the nucleus doesn't break up, so it produces 0 neutrons. And we measure this using the ATLAS 0 degree calorimeters. These are far forward detectors that measure neutrons that are emitted by the nuclei kind of down the beamline after they've collided. And you can see kind of we get a very clean measurement. So you see a large signal for single neutrons. So one neutron is very visible in the ZDC, 2 neutrons, 3 neutrons, and then a continuum. In general, you don't expect a huge number of neutrons to be produced, but you have oftentimes more than one. So the really important thing about the neutron measurement, though, is that it tags which side of the detector had the nucleus which was struck, and which side tells you, and which side had the photon emitted. So the first thing that we do by being able to tag the 0, n, and xn sides of the detector is choose unambiguously which side is photon going and which side is nucleus going. And for the rest of the results I'm going to show, that photon going side is always oriented in the positive direction, and the nucleus going side is always oriented in the negative direction. So then we require that there be jets. So the photonuclear jet measurement, we care about jets. So we look for at least 2 of them. As you'd expect, you're able to have more than 2, so all of our kinematic variables are going to be defined. In the case of n jets, you just need at least 2 for the event to be tagged. We require them to have PT greater than 15 GeV. And then using the jet kinematics, we reconstruct kind of 3 variables that are relevant here. So these are HT, XA, and Z gamma. So HT, I mentioned before, is the linear sum of all of the jet transverse momenta. You can think of this as the proxy for the Q, the hard scattering momentum scale in our hard scattering process. XA is kind of a proxy for the Bjorkane X in a 2-to-2 scattering picture. To higher orders, it's not exactly that, but it's a pretty good proxy for our purposes. So this is effectively our Bjorkane X variable for probing the parton distributions. And then Z gamma is kind of very technically stated, it's the energy that the photon carries into the hard scattering process as a fraction of the emitting nucleus's energy. Okay, you can think of this effectively as a fractional proxy for the photon energy. So higher Z gamma is a higher energy emitted photon, lower Z gamma is lower energy. It convolves that with the potential fraction of the total energy that's carried in the case of a resolved photon. So Z gamma rolls up kind of the photon flux effects and the resolved photon energy fraction effects all into one variable. So it's both. So once we have our jets, we can do the last event selection, which is certainly the most challenging, and that is to require gaps. So because this is an inclusive process, we have to require gaps. Now, normally in the table that I showed a few slides back, going through all of the different UPC measurements that exist, right? You have vector meson production, dilepton production. In all of these cases, you don't expect anything else to be produced in the detector. So you make your life really easy and you veto any event that has anything besides what you care about. Now, we don't get to do that because we break up one of the nuclei. We fully expect there to be other particles in the detector, but we only expect there to be other particles on one side. So you can see that we have lots of particle production on the nucleus going side of our jets and very little particle production on the photon going side of our jets. Now, it's possible to have some small amount of particle production on the photon going side because you have a resolved photon. So that can cause a bit of hadronic particle production filling that gap, but it's a fairly small amount. So there are 2 variables here that are relevant for doing these gap selections, for requiring that you have large amounts of empty space in the detector. The first is what I've drawn down here, sum delta eta on the photon going side. So this is, we denote it as sum gamma delta eta. This is where you take all of the gaps in rapidity between particles that are greater than half a unit and you add those up. So in the case of our example diagram, it's the sum of the 2 green gaps. You add those up and that gets you the sum of gaps. And the idea of this variable is that it's very resilient to detector noise. If you have a particle that's in fact not a real particle, but a noisy cluster in the calorimeter, that's not going to break up the sum of gaps in the way that it would if you looked at the gap just to the first particle. And it's also going to be resilient to the resolved photon. So it's not going to reject these resolved photon events, which we want to be able to see. And then the other variable that's relevant is the edge gap. So this is the edge gap. It's denoted on both sides of the event. The one that's particularly relevant for us is on the nucleus going side. So you expect the nucleus going edge gap to be very small. You're going to have particle production all the way up to the edge of the detector. So you can use this as kind of a variable just to make sure that you're vetoing anything that doesn't have quite the right alignment. I'll talk a little bit more about why we care about that variable later on. So when we do our gap requirements, we can construct this kind of a distribution on the upper right, where I'm showing you the photon-going sum of gaps, this variable I talked about here with the sum of the green, and that's plotted against the charged particle multiplicity in the event. So this is just the total number of particles in the event. And the thing that you can see, right, is that you have a characteristically different distribution at small sum of gaps compared to large sum of gaps, okay? And if you make a cut at 2.5, which is our selection that we use in the analysis, you can see you pretty cleanly separate this very steeply falling multiplicity distribution, which is characteristic of our photonuclear events, that gets separated from this very wide multiplicity distribution, which corresponds to a hadronic background event set that we're throwing away. Okay. Okay. Now, the real question is, how well does this cut perform? This is a precision measurement. We're interested in teasing out nuclear PDF effects on the order of a few percent. So we need to really tighten the screws on this measurement and make sure that the selection we're applying is actually doing what we expect it to. So the way that we handle this is through a template fitting procedure. So we take our measured gap distributions, shown as black circles, and we represent them as the sum of 3 different contributions here. One contribution is the hadronic background. So this is the distribution which has small values, or which is peaked to small values of the sum of gaps. So it's very small gaps, and it falls steeply. The reason you get large sums of gaps in hadronic events is purely just due to fluctuations in the particle production. So it's very rare. This distribution falls steeply, but because there's so much hadronic background, you're still able to get some substantial leakage into your signal region if you're not careful. And then in the larger gap region, the distributions are given by direct and resolved Monte Carlo, which are separated out. Now, because the gaps are modeled really effectively in this measurement, by separating the direct and resolved Monte Carlo, we're actually able to let their relative contributions float. And through this template fitting procedure, actually understand something about the structure of the photon that's entering into these processes. So using these template fits, the first thing we can do is test out the selection that we're applying. So here I'm showing 3 different potential sum of gaps cuts. In blue, we have kind of a tighter cut than the one we actually apply. In black, we have a looser cut. You can see the loose cut lets in a huge amount of background, 6% of the total sample in our highest Z gamma bin, whereas the red reduces it massively, and then the blue is a very tight cut, so it reduces it a bit more. But within the level that we care about, our 1%, a 1% background is an acceptable level given the systematics on the measurement. So we select the 2.5 cut. And then, as promised, we can, I think, in a way that's really something we didn't expect to be able to do when we first started trying to do this measurement, by allowing those direct and resolved contributions in the template fit to vary to describe the data as well as possible, we're actually able to extract the relative contributions of direct and resolved processes. So in this case, I'm showing the direct fraction, and we're plotting this using template fits as a function of Z gamma for each of our different HT bins. So this is giving you information about the actual structure of these quasi-real photons and how well the photon PDFs plus the modeling for Pythia is actually describing the hadronic structure of the photon. So this isn't a full-blown measurement. There aren't full systematic uncertainties or anything like that. But I think what we're showing here is that the level at which we're able to model these gap distributions, just kind of out of the box, this is the first measurement of its kind, is already good enough that we're able to kind of look at extracting this kind of physics from the data, which is really exciting. So then, as I mentioned before, this is an oddity that I just wanted to highlight. So this edge gap on the nucleus going side, you would expect this distribution to fall very steeply. In a photonuclear collision, you don't really have any gap expected from the broken up nucleus to the first particle that's produced. You should have consistent particle production over that range. And that's exactly what we see, right? So if you look at kind of this low Z gamma interval of the template fit, we have basically this very steeply falling particle production or edge gap distribution, right? So if this falls off very quickly, there's maybe some contribution from a background in the tail, but it's not obvious, really. It could just be nothing. But the oddest thing happens when you start to look at higher and higher Z gamma, which is in the more and more mid-rapidity region of the detector. Okay, so you're closer to mid-rapidity in these cases. And that is that you get contributions that are not described by the tail of your regular photonuclear jet production. Right, so this red distribution cuts off, and then you see that it picks back up the data that we measure. And this, we initially thought that this could be described by looking at for things like 2-photon production of a QQ bar pair, so you have large gaps on both sides, or diffraction, potentially you're striking a coherently produced pomeron in the struck nucleus. None of those models describe what we see. The thing that describes it almost perfectly is that you have photonuclear jet production, but the ZDC is wrong. So you effectively flipped the neutron direction of the event. This is very unexpected for us because in the picture that we're telling, right, you have this hard scattering process where the photon strikes one nucleus, it breaks up that nucleus, it rips a parton out of it, causing it to break up, and you always would get neutron production on that side, and you would never get neutron production on the other side. So the thing that we find, though, is that if you look at 0n, 0n, so no neutrons on either side, you see a surprisingly large contribution from photonuclear jet production, which doesn't really make much sense. So we're still trying to understand exactly what this is. We believe that it's possible that the photon strikes a nucleon near the edge of the nucleus, potentially a neutron in the skin, and produces jets in a photonuclear collision that somehow doesn't perturb the rest of the nucleus enough to produce neutral fragments in the forward region. But what can also happen in these events is that you get additional breakup due to secondary electromagnetic interactions, which gives you ZDC contributions, which produces backwards events in our 0nxn class. So the way that we veto these backwards events is with this nucleus going delta eta edge gap requirement. So this is very surprising to us while we were doing the measurement. It ends up being a fairly important cut. If you don't apply this selection, your highest Z gamma bins end up getting a lot of background in. But once you kind of apply a fairly basic selection, you throw away this background quite effectively. Yeah.
How should I understand the fact that the ZDC problem gets worse at higher Z gamma?
Yeah, so it actually makes sense. So the way to think about Z gamma, let me see, this is my next slide. Let me skip just, hold on. Yeah, so this guy. So let's see. This is just a rapidity distribution of the our signal. So the thing that you can see is that high Z gamma, that's this region near mid rapidity right here. So this is kind of our high Z gamma region where you're right in the tail of the photonuclear jet production. If you flip this distribution, it's going to be peaked right there. So you naturally expect if you reverse the events, all of your background is going to show up right on the tail because that's where the peak of the flipped distribution is.
Oh, okay.
Yeah. So it's just kind of the relative contribution to background and signal works out that way. Oh man. I'm really, see if I can. Okay, great. Yeah.
Before you go on, can you say something about this glitch at 1.8 or so?
1. Oh, sure. This is ATLAS detector structure.
Okay.
So at 1.8, we transition from the Ford calorimeter to our hadronic end cap. So you see a change in the energy scale for the clusters that you measure. So it's just, that's just purely, this isn't, an unfolded variable or anything like that. So it's reconstruction. So spent a lot of time talking about the interesting physics of photonuclear events. The actual experimental challenge of this measurement gets one slide, which is jet reconstruction. So this is a very odd collision system as far as ATLAS is concerned. It's very low activity. So the jet measurement in principle should be pretty straightforward, but jet calibrations are a bit of a mess. So the nice thing about this UPC collision system is that you have very little background, so there's nothing stopping you from going to very low jet PT. So we extended this measurement lower in jet PT than ATLAS has ever gone before. I believe this is the lowest energy calorimetric jet measurement ever done at the LHC. I don't want to make any claims for other experiments that aren't mine, but for ATLAS, I know that's true. So we do a full jet calibration. And the thing that I really want to highlight about this is that kind of if you get into the nuts and bolts of the way that we calibrate jets in the photonuclear case, it's very similar to the kinds of jet calibrations you're going to want to do at the EIC, at the Electron Ion Collider, which is planned. And in fact, when you go to connect the data set, when you go to compare data from the UPCs at the LHC to data at the EIC, the dominant sources of jet uncertainty are largely going to be shared between the two. The dominant jet uncertainties that you get come from modeling of the jet fragmentation and how your calorimeter responds to that. And those same fragmentation modeling uncertainties are also going to be dominant sources at the EIC. So when you go to compare these measurements, you're actually going to have correlated uncertainties between the two. So we're really learning right now kind of about how to do jet measurements at the EIC by doing them in UPCs at the LHC. And here I'm showing just the total systematic uncertainty that we have in kind of measuring the relative energy scale throughout the whole detector as a function of the jet eta and the absolute energy scale uncertainty as a function of jet PT. So once we calibrate our jets, we can look at about how well these events that we've selected with our jet calibrations compare between data and Monte Carlo. So I want to use this to highlight some features of the Monte Carlo sample that I'm going to be comparing to later on. So the first thing I want to say about it is that, like I mentioned before, these events are highly asymmetric. So if you look at the rapidity distribution of your jet production, it's highly peaked towards negative values since we align the photonuclear jet cloning system so that the nucleus is going in the negative direction. Okay. And then at large negative values, you have, these are very large XA and very small Z gamma. And then kind of when you're in the positive Y jets region, right in the tail of the distribution, that's where XA is at its very smallest and where Z gamma is the largest. And that's the region where we expect to be most sensitive to uncertainty and nPDF effects in the nuclear shadowing. Then the HT distribution, so the distribution of the sum of the jet PT, largely agrees pretty well. And then I think something that's important to remember is that all of the comparisons I show are going to be to Pythia Monte Carlo. So Pythia is a wonderful generator. It gets a lot of things right. It models the gap distributions great. It's only leading order. So the thing to keep in mind is that you get the two-jet contribution beautifully, but then the data overpredicts the Monte Carlo for all of the higher jet multiplicities exactly like it should. The data is not a fixed order calculation. Pythia is. So you're missing kind of these higher order multi-jet configurations. So we're going to expect Pythia in particular to slightly underestimate the data because it's missing those NLO contributions. So that's just something to keep in mind going forward. So next, this is a jet measurement. Oh, never mind. Oh. I'll give that line in a second, but we have one other piece with the kinematic distributions, which is the kinematics of these systems have important correlations which are introduced by virtue of our event selections. So we require at least two jets with PT of 15 GeV. That puts a hard minimum on the total amount of energy that's in the event. So you can see if you look at the correlation between XA and Z gamma, when you measure a certain value of Z gamma, that selects for a certain photon energy, and that restricts the range of parton energies you're able to measure. So if you don't have much energy coming from the photon, you can only really see high energy partons that you strike in order to pass the kinematic requirements. Similarly, if you go to very high photon energy, you get all the whole range, but you're really dominated by the low energy partons. So you have kind of this selection effect that's introduced in one variable by virtue of what the other is. The same isn't true for HT. So generally you can see kind of for a given value of XA or a given value of Z gamma, it's really just kind of the statistical, the distribution kind of falls off based on the statistics that you have with the overall XA or Z gamma distributions. So you can measure kind of XA for different values of HT without really worrying about introducing a bias. But if you measure for different values of Z gamma, you're very clearly biasing what ranges in XA you're able to see. So it's something you need to keep in mind, which we'll talk about a bit more in kind of our strategy for understanding the data later on. So It's a jet measurement, which means that you have a large amount of experimental resolution on the kinematics that you're measuring. So we have to unfold our data. We handle this unfolding in a three-dimensional way, in particular because with XA and Z gamma, they're both exponentially enhanced by the jet rapidity. So you're quite, the response in one, or the value of one dictates which region you're at in the detector for the other. So it's going to tell you a lot about its given response. So you have to unfold this measurement in 3 dimensions, HT, XA, and Z gamma. The thing that you're unfolding for is the jet response. So on the left here, I'm showing the jet energy scale, or the mean closure of the jet energy measurement. You can see that it's typically quite well closed, affects to less than 0.5%. In basically all of our rapidity intervals, aside from this gross one where you're at a transition point in the calorimeter. And our jet energy resolution, I really want to highlight because it's kind of crazy. You don't really get resolution this good for calorimetric jets. It's really because we're doing particle flow in ultra-peripheral collisions where the event's really clean. We see, kind of near the middle of the detector, you have 12% resolution at 15 GeV, which is just not really how anything works when you're looking at high pileup or heavy ion collisions or anything, or hadronic PP, anything like that. We're really able to get kind of the best jet performance that you can see at the LHC in these collisions because of the unique environment of UPCs. So it makes it a really high precision jet measurement in a way you can't really do otherwise. Yeah.
Basically, then the particle flow is not kind of standard method in ATLAS in hadronic interaction.
So it depends. Particle flow it wasn't at first. So ATLAS in run 1 and run 2 did mostly just cluster-based jets. They started transitioning to particle flow, so it's become totally standard on the PP side. On the ion side, we still don't really trust it in lead-lead collisions. So we still do calorimeter only jets for lead-lead. But it's at this point pretty much standard for PP. But it does not get resolution anywhere near this good. Yeah. So let's see. All right, so that's our jet performance at a basic level, but what does that translate to in terms of the actual experimental uncertainties? So these are the things that are dictating our actual ability to measure nuclear PDFs. And in spite of all of our work on jet calibrations, we're still completely dominated by the jet uncertainties, which is to be expected for jet measurements. So in particular, the jet energy scale uncertainties, which are shown in magenta here, are dominant uncertainties over the full range of XA for each of these different HT intervals that I'm showing. Second is the jet energy resolution, which again is much smaller because we get such good resolution on these jets. So we're not as sensitive to it. You also have uncertainties that arise due to the gap selection and the unfolding performance, but those are typically subdominant. The really nice thing about jet uncertainties, though, is that they're very highly correlated bin to bin. So here we're looking at, kind of in the best places we have, 5% total systematic uncertainties, typically less than 10% if you look at the total value. That's enough to constrain nPDFs. But since our systematic uncertainties are so highly correlated bin to bin, there's actually much more information that you can get out of the measurement. So by taking into account these correlations, which I'll do on the result plots that we show, you're able to get much higher precision and really pin down the nPDFs in a more meaningful way. So let's see. A brief aside before I show you the results, that is on nuclear breakup. So I mentioned this before with the problem events of having the ZDC not correspond to the correct direction. But something that's generally true is that this picture of nice 0n xn photonuclear jet events where the photon emitting nucleus doesn't break up, the struck nucleus does, it's totally wrong. It's not totally wrong, but it's incomplete. So our naive picture of a photonuclear ultra-peripheral collision is one like I've shown on the right here, where you have a large separation between the nuclei, a photon from the co-moving electromagnetic field strikes the nucleus, and it breaks up that nucleus. But we're looking at incredibly high energy photons here. We need at least 2 15 GeV jets. You're producing a large amount of energy. And because you have so much energy in the event, you require such a large photon energy, those photons really only occur right in the part of the flux that's very close to the photon emitting nucleus, since the energy falls off so steeply with impact parameter. So what this does is it biases us towards small impact parameters where you have a near passing collision. And what that means is that as a function of your photon energy, the rate at which your events don't break up falls off dramatically. So for small z gamma, we measure this fraction, the non-breakup rate. This is effectively the events which actually have a 0 and xn topology instead of there being some additional interaction which breaks that up. So we measure this, and you can see that kind of for the lowest z gamma, the lowest photon energy, you have about an 80% non-breakup rate. So that about recovers the probability that you get in gamma-gamma or exclusive vector mesons at low mass. And then at high z gamma, we get a non-breakup rate of like 30%. So 2/3 of the events break up for our highest z gamma event. So you see this really large variation that comes from this impact parameter bias in the photon flux that you have to be really careful with. So we have to, we measure this fraction, we apply systematic uncertainties, or we compute full systematic uncertainties, and we get a measured, smoothed band here, which I show in red, which we use to correct our data in order to be able to compare apples to apples, the non-normalized cross sections between data and simulation. There have actually, since we kind of brought this up a while ago, there have been some theoretical calculations of this that actually describe the breakup rate surprisingly well. So there are a couple of different ways of modeling the nuclear charge distribution that are shown as the purple and green lines here that actually do a surprisingly good job of describing the data. So this is actually pretty theoretically well understood too, which is good. It implies that this won't be an obstacle in actually being able to extract the nPDF effects that we care about. So, all right, that's everything we need. Let's start talking about the results. So, like I mentioned before, when you pick a particular value of z gamma, that restricts the range in XA that you're able to see. So the way that we're going to go about doing this measurement, since it's triple differential in z gamma, XA, and HT, is by selecting bins in z gamma. So on the left here, this is the z gamma distribution in different slices of HT. And by selecting a particular value in z gamma, by selecting one of these bins, that then maps onto a distribution in XA where you're effectively removing your sensitivity to most of the region where you're integrating over these selection effects. So you're looking at these finer slices in XA, which are actually representative of the effects that arise due to nPDFs, compared to just kind of integrating over this edge that occurs over the full range in the distributions. So let's scan in photon energy. So if we start at intermediate photon energy, you can generally see, first of all, just strikingly good agreement. This is the first measurement of photonuclear jet production in UPCs. And for the most part, the data agrees with the Monte Carlo predictions to about 10% in this region. So that's about on the scale that we would expect. There are going to be NLO corrections on top of this, which you would naively expect to be maybe 10 to 15% or something like that. So I think you need to be careful before drawing too strong conclusions about the size of the nPDF modifications from this data. But I think the agreement from the outset, when you look at intermediate z gamma, is quite good. The other thing I'll say is that in the bottom panels of these distributions, so actually, let me take a step back and describe what's going on with these plots. These are how we're styling our result plots. So we're showing the triple differential cross sections in the upper panels. These are for a given interval in z gamma. These are different slices in HT, the XA distributions, with the dashed lines overlaid for the Pythia prediction with NCTEC 15 PDFs. So then in the bottom panels, we're showing the ratio of the theory over the data. And then I'm separating out the part of the systematic uncertainty that's fully correlated across all of the bins, that's shown in red. And then the remaining systematic uncertainty is shown in gray with statistical uncertainties in yellow. And this is the consistent plotting convention throughout all of these result plots. The thing that I'll note about this is that, like I said before, we had these large systematic uncertainties. If you look integrated over the flow range in z gamma, when you actually separate them out, you have individual bins where the typical systematic uncertainty is a few percent. It's often as low as 1% or 2% once you account for the actual correlation in systematics. So these correlated effects are easy to take into account when you go to constrain nPDFs in a fit. So we're really looking at, kind of 1 to 2% level constraints in a lot of places on nPDFs from these results. So if you start looking higher in photon energy, you see that we start to lose access to some of our bins at higher XA, but you start to open up the lower X region and probe lower and lower in X with your measurement. So again, the level of agreement is still quite good in this region. In general, the theory underpredicts the data, which is about what you would expect since we're missing the higher order contributions with the leading order calculation. And then if you look even higher in Z gamma, again, the consistency isn't quite as strong for the very highest Z gamma region. In part, that has to do with the nPDF effects being more uncertain here. We're measuring the very lowest XA region that we're able to see where we're really sensitive to uncertainty in the nuclear shadowing. So in general, we have quite good consistency. The experimental uncertainties are a bit harder to control in this region. So we have larger, oftentimes 5 to 10% uncertainties in a lot of these bins. But we're able to really access all the way down to, in kind of our lowest X region, 2 times 10 to the minus 3 in XA is the lower bound of the lowest band in the measurement. So if we sum up all of the different Z gamma bins, we don't get as robust of a separation of the correlated uncertainties, but we get a broader picture of kind of how the consistency between the data and the theory looks for all of our different intervals. So here's for 4 different HT intervals, the consistency between data and Monte Carlo. In general, the thing you can see is that with the NC Tech PDFs, you have kind of broad agreement at low HT in the anti-shadowing region here at intermediate XA, and then kind of an under prediction by the theory by about 10 to 15% in the lower X shadowing region. And then it kind of flattens out when you go to higher XA. There's some structure here, but within the uncertainties, it's not so obvious what the trend is. And then I think, somewhat interestingly, we can look at just the ratios, but compare a bunch of different nPDF fits. So here I'm showing 4 different models for the nPDF. The black is the NC Tech that I showed on the previous plots. Blue is the EPPS model. Red is nNPDF. Green is this 2U model, which is a specifically NLO nPDF fit, which has to use a lot less data because it only uses NLO calculations. In general, broadly, the thing that you can see is that you have even more under prediction by EPPS and nNPDF in this in the shadowing region in the lower HT bins. Interestingly, these are the 2 fits that include data from P-led dijets at the LHC. So those seem to underpredict in this shadowing region. Then they're kind of broadly consistent in the anti-shadowing region. Then when you go to higher XA, it's a bit less obvious. I'll say that the theory you naively expect to flatly underpredict the data because you're missing the NLO part of the calculation. So you don't necessarily want to extract nPDF effects just by eye. But in general, you have kind of agreement with the nNPDF at higher XA and kind of flat underprediction by most of the other models in this higher HT region. So in conclusion, the data that we're able to get from photonuclear jets is broadly providing a high level of constraint over a wide range of X and Q squared, which is not well constrained by existing data. These should be able to provide a substantial amount of constraint to nPDFs once there's a good NLO calculation to compare to them, which we're talking to theory colleagues about day to day. So that should be on the way soon. And again, by treating the full systematic uncertainties we're able to do through kind of a deep knowledge of the jet systematics and the jet calibrations, we're able to provide a lot of constraining power on nPDFs. One last thing I'll note is that if you compare our coverage to projected EIC coverage for nuclear parton distributions, our measurement overlaps with the high Q squared LHC data, but it also overlaps with projected EIC coverage in a meaningful way. So it's going to be able to both provide a reference for what you'd expect to see at the EIC directly and a comparison to LHC data to be able to kind of bridge between these 2 regimes. So UPC plays a really interesting role in that regard. So thanks. Happy to answer any questions.
Questions? I have some. First of all, why did you use HT for the Q squared proxy instead of the jet mass?
It's a good question. In part because so in kind of dijet measurements that are broadly used for nPDF calculation or for input to nPDFs, the hard scale is typically the average PT. We wanted a variable that generalized better to multiple, to more than 2 jets, you kind of for higher order calculations. So I think HT followed naturally as an extension in that way. The other thing that I would say is that it maps more cleanly onto our event selections, which is a useful property when you go to unfold.
Can you look into substructure of those jets or study some sort of characteristics?
Yeah, absolutely you could. So if I go, so the real thing you would want to do here, right, is, oh, I went too far. Really what you would want to do would be have the good angular resolution that you get from looking at tracks. So within ATLAS, we can do that from -2.5 to 2.5. So broadly, you have a lot, you don't have the full spectrum within the tracker, but you have a lot. So kind of with run2 data, you can absolutely do substructure on UPC jets. I think this is something we would be doing right now if the ATLAS heavy ion group were larger. But in principle, right, you could kind of test out planned substructure measurements at the EIC in UPC in a way that's basically analogous. Yeah, and then when ATLAS extends the tracker in run 4, you'll be able to do it over kind of the full UPC jet acceptance.
Wait, I have one more. I want to ask about the trigger setup. So you have a note here, 1.72 inverse nanobarns.
Yeah.
Inverse nanobarns. Well, how does the trigger works currently?
So, well, currently versus run 2 are different.
Well,
Yeah,
what's
for
the data
for the
show?
run, yeah, for the run 2 data.
But please explain how it's current as well.
Yes. So, okay, the run 2 data where everything was beautiful and nice. We have at level, so we do ATLAS does a 2-tier trigger system, hardware and the software. For the hardware-based trigger, we have 2 requirements. One is a ZDC XOR, so 0 and XN in the ZDC, and a minimum ET threshold in the calorimeter, so at least 5 GeV of total transverse energy. That lets us basically sample the full luminosity. I think one of our triggers was slightly pre-scaled for part of the run, so it's 1.72 instead of 1.76, which was the total ATLAS.
Then I guess
ready.
you need to have a very high projection on software trigger. This looks like
Yeah,
you'll be collecting a lot of these.
So we have an HLT jet requirement, sorry, a software jet requirement, which vetoes a lot of events. So the combination of the rejection, in run 2, the level 1 calorimeter total energy requirement was very good. It threw out basically all of our noise, and you ended up with kind of a nice, nearly min-bias photonuclear sample. And then the high level trick, the software jet requirement lets you kind of very cleanly take these events. Currently, ATLAS has upgraded its level 1 calorimeter trigger.
So it's much better.
For other people. I think some ATLAS doesn't necessarily think about low PT physics so much. So an upgrade for them is a bit of a downgrade for us.
Join Alice.
Yeah, but then I don't get all this rapidity coverage.
Join Alice 3. Okay, so currently is what?
So currently
they go for
so it's
beyond standard model and
yes, and it's way noisier now. Okay. So doing kind of
it's because of the pileup or
no, it's so the technical reason is that they used to do cuts on the analog calorimeter signals for the level 1 trigger. Which was really good for a total energy requirement because kind of prior to digitization, you get a lot of sensitivity. But now they digitize and then apply all of the thresholds. So we are kind of digitizing, applying noise cuts, and then kind of summing everything. So that process is much worse at rejecting low PT noise. So there are ways that you kind of, our level 1 calorimeter people.
But hold on, I understand you're actually not losing those interesting events, but you have to seek more, do more effort to find what.
Yeah, so it's not that we can't find them.
That's not bad. I mean, It's worse, I
Yeah.
agree, but it's not.
I think at the moment, we haven't found a way that kind of with this style of digitizing the trigger, we haven't found a way to get to reproduce the same performance that we got in run 2. It's not that we can't do this measurement anymore. It's that kind of this, I think we were spoiled by the run 2 performance a little bit. And now we're having to work a bit harder, but I think in 2024, when they applied the upgrade, I think it was a little jarring, but in 2025, we're prepared for it. So I think we'll be able to tune it much better, even if we don't get the full performance we have in run 2.
Can I ask a technical question? So you show us the template fit, and the green one was hadronic, the one from the hadronic interaction. So can you remind me how you obtained this green one?
Was it the green? Let's see.
Yeah, this one.
Oh, this one.
Or the,
But I think the other one.
Yeah, the other one.
Yeah.
Right.
Oh, yeah. So, the magenta? from
Right,
Hadron?
magenta.
Yeah. So it's a mess, actually. So what you would really want to do, if you were being kind of as clever as possible about this, would be use P-LED data, because that'll get you kind of the closest thing to a hadronic multiplicity distribution with the relative rates of diffraction and hadronic interactions that are actually making up our data here in lead-lead. But for kind of technical reasons, we couldn't use P-LED data. So instead what we do is we use PP data at 5 TeV. But the PP data has a relatively higher contribution from diffractive processes than lead-lead would. So we use a cocktail of PP data and hard scattering PP Monte Carlo that we allow to vary in the template fit to kind of optimally describe that distribution.
Is it also due to the fact that the lead-lead, even the global failed to describe the tail of the centrality distribution, or?
It's definitely possible. These are weird events, right? These are hadronic events where you're not producing neutrons in one of the ZDCs.
Mm-hmm.
So I don't think that, I think that Monte Carlo modeling of them I would not expect to work particularly well. You can't use peripheral lead because you have photoproduction, right? So you need some sample where you don't get, the gamma A rate.
Right.
So PP data has that, so we're able to use it, but we have to kind of do this add-on to kind of get it to actually model the region well.
Mm-hmm.
I have maybe last question.
Yeah.
About the results where you say, you underpredict the leading order, and you need an NLO calculation. Are people working on that, either the people who do NLO fits or somebody in ATLAS?
Yes, there are multiple people working on that. So the nice thing that I really like about this measurement is that the hard part is kind of on the experimental side. So the NLO jet production calculation there are a lot of calculations that currently exist that are published. So the calculation has been done for a little while. So there are groups that do NLO or that do nPDF fits that have their own calculations who are comparing to the data. And actually Sherpa, the NLO parton shower Monte Carlo model, recently came out with a version that actually does parton shower matched NLO jet photo production. So you could even, I think that, the nPDFs don't want to include a parton shower matching in their fit, but in principle, you have even higher order predictions that are possible.
Okay. Any last questions? If not, let's thank Ben again.